Since the dawn of its existence, humanity has gazed at the heavens in awe, striving to uncover the mysteries hidden behind the stars and galaxies. This infinite expanse has always been the source of our curiosity and our drive for exploration. Yet everything we know, see, and touch constitutes only a tiny fraction of the universe. The fascinating structure of the observable cosmos, planets, stars, galaxies, and those shimmering clouds of cosmic dust, actually makes up merely 5% of the total content of the universe. So, where is the remaining 95%? This question reveals one of the greatest and most enigmatic riddles of modern cosmology: dark matter and dark energy. These invisible forces shape the fabric of the universe, bind galaxies together, and accelerate the cosmic expansion. We cannot observe them directly because they do not interact with light or any other form of electromagnetic radiation. However, their existence has been scientifically proven through their gravitational influence and their distinct effects on the dynamics of the universe. In this documentary, we will attempt to illuminate the dark side of the universe, exploring what dark matter and dark energy are, how they were discovered, and how they influence the future of the cosmos. These mysterious components, which push the limits of science, hold the potential to transform our understanding of the universe at its deepest level. Get ready, for we are embarking on a journey into the universe's most profound secrets. Our modern scientific understanding of the origin of the universe is based on the Big Bang theory. Approximately 13.8 billion years ago, the universe began expanding from a state of extreme density and heat, a singularity. This expansion continues to this day, proving that the universe is constantly growing. However, the discovery that the universe's expansion is not merely continuing but actually accelerating was one of the most astonishing revelations in cosmology. The driving force behind this accelerating expansion is what we call dark energy. The first clues to the existence of dark energy appeared in the late 1990s through the observation of distant supernovae. Two independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, used Type Ia supernovae to measure the rate of cosmic expansion. Type Ia supernovae occur when a white dwarf star exceeds a specific mass limit, the Chandrasekhar limit, and explodes. These explosions always have the same intrinsic brightness, making them reliable standard candles for measuring cosmic distances. By measuring their apparent brightness, the teams could determine how far away these supernovae were and thus infer the expansion rate of the universe in the past. However, contrary to expectations, both teams found that the distant supernova appeared dimmer than predicted. This meant that they were receding from us faster than expected. In other words, the expansion of the universe was accelerating, not slowing down. At first, this shocking result was met with skepticism. Scientists spent months verifying their data and checking for potential errors in their analyses. But the results remained consistent. The universe was indeed expanding at an ever-increasing rate. This discovery revolutionized cosmology and led to the naming of the mysterious force behind this acceleration: dark energy. For this groundbreaking work, Perlmutter, Schmidt, and Rees were awarded the 2011 Nobel Prize in Physics. Dark energy constitutes about 68% of the universe and is a uniformly distributed repulsive force. Unlike gravity, which pulls matter together, dark energy pushes space apart. The most common theory suggests that it represents a form of energy intrinsic to space itself, the cosmological constant. This concept, originally introduced by Albert Einstein in his general relativity equations and later called by him the biggest blunder of my life, regained significance after the discovery of the accelerating universe. Einstein had included it to counteract gravity and keep the universe static, a notion later dismissed after Hubble discovered the universe was expanding. Today, however, the cosmological constant re-emerges in the form of dark energy. Yet, A massive discrepancy remains between the amount of vacuum energy predicted by quantum mechanics and the amount of dark energy observed, a difference so vast that it exposes our fundamental lack of understanding of dark energy's true nature. The enigmatic essence of dark energy continues to be a central topic of research and debate within the scientific community. Various cosmological models attempt to comprehend its effects on the fate of the universe. Current observations suggest that the density of dark energy remains relatively constant, implying that the universe may be heading toward a big freeze scenario. In this scenario, the universe will expand forever, becoming colder, emptier, and darker with time. Stars will die, black holes will evaporate, and only photons and elementary particles will remain. A state of cosmic solitude that provokes profound philosophical questions about humanity's place in the cosmos. However, if dark energy grows stronger over time, the expansion could accelerate to such an extent that galaxies, stars, planets, and even atoms would be torn apart, a scenario known as the Big Rip. Conversely, if dark energy weakens or gravity prevails, the universe's expansion could slow down, eventually reverse, and end in a big crunch. These alternate fates highlight the critical role of understanding dark energy in predicting the ultimate destiny of the cosmos. Another major mystery of the universe is dark matter, which makes up roughly 27% of the cosmos. Its existence was first proposed in the 1930s by Swiss astronomer Fritz Zwicky. While studying the Coma cluster, Zwicky noticed that the galaxies were moving much faster than their visible mass, stars and gas, could account for, yet the cluster remained bound together. This indicated the presence of an unseen mass exerting gravitational influence. His revolutionary idea was largely ignored at the time, but later observations would confirm his insight. In the 1970s, more compelling evidence came from Vera Rubin and Kent Ford, who studied the rotation curves of spiral galaxies. They observed that stars in the outer regions of galaxies rotated almost as fast as those near the center, a result inconsistent with Newtonian mechanics and visible matter distribution. This inconsistency suggested that galaxies were surrounded by vast, invisible halos of dark matter, which provided the gravitational glue keeping them intact. This became one of the most convincing pieces of evidence for the existence of dark matter, fundamentally shaping the course of cosmological research. Additional support came from the phenomenon of gravitational lensing, the bending of light around massive objects. When scientists analyzed how galaxy clusters distorted the light from background galaxies, they discovered that far more mass was present than could be accounted for by visible matter alone. One of the most famous examples is the Bullet cluster, a pair of colliding galaxy clusters. Observations showed that the dark matter passed through the collision unaffected, separating from normal matter, and offering direct evidence that dark matter behaves differently and far more exotically than ordinary matter. Since dark matter does not interact with light, it cannot be detected directly. Scientists are therefore searching for the particles that make it up through various experiments. One leading hypothesis involves weakly interacting massive particles, WIMPs, theoretical particles that formed in the early universe and interact only via gravity and the weak nuclear force, but not electromagnetically. To detect them, scientists have built massive underground detectors shielded from cosmic rays. Experiments at facilities such as Italy's Gran Sasso National Laboratory and the U.S. Sanford Underground Research Facility, notably the LUX Zeppelin (LZ) experiment, aim to observe the rare collisions between WIMPs and atomic nuclei, which would produce faint flashes of light or ionization signals. However, to date, no definitive evidence of WIMPs has been found, prompting researchers to explore alternative candidates such as axions and sterile neutrinos. Axions are extremely light particles proposed to resolve issues in quantum chromodynamics, while sterile neutrinos are hypothetical particles that interact only through gravity. These alternatives strengthen the idea that dark matter might be more exotic and complex than previously imagined. Searches for dark matter extend beyond underground detectors. Scientists are also pursuing indirect detection methods and particle accelerator experiments. Indirect detection focuses on identifying gamma rays, neutrinos, or other particles produced when dark matter interacts or annihilates. Instruments like the Fermi Gamma-Ray Space Telescope and large neutrino observatories look for such signals from regions with high dark matter density, though distinguishing these from astrophysical noise remains extremely challenging. At the Large Hadron Collider, LHC, at CERN, physicists attempt to produce dark matter particles in high-energy collisions. If these particles exist within the collider's energy range, they might carry away energy and momentum, leaving behind detectable imbalances in the data, a potential sign of dark matter production. Although no dark matter particles have yet been directly created, these ongoing efforts push the boundaries of particle physics and may one day yield a breakthrough. Dark matter and dark energy form the foundation of the LCDM, Lambda-Cold Dark Matter model, the standard cosmological model that successfully explains the large-scale structure of the universe and the formation and distribution of galaxies. According to this model, about 5% of the universe consists of normal matter, atoms, planets, stars, 27% of dark matter, and 68% of dark energy. These proportions align remarkably well with multiple independent observations, including the cosmic microwave background, CMB radiation, supernova data, and galaxy cluster surveys. The CMB, the afterglow of the Big Bang emitted about 380,000 years after the universe's birth, holds vital information about the early distribution of matter. Precise measurements by missions such as the Planck satellite have determined these cosmic proportions with extraordinary accuracy. However, while the LCDM model describes how dark matter and dark energy influence the universe, it does not explain what they are. This limitation drives physicists to explore new theories beyond the standard model of particle physics. Concepts like string theory and extra dimensions offer intriguing possibilities. String theory proposes that all fundamental particles and forces arise from tiny vibrating one-dimensional strings, while the idea of extra dimensions suggests that dark matter could exist in hidden spatial dimensions beyond the familiar three. Though these theories remain speculative, they expand our imagination and open new paths of inquiry, bringing us closer to a more unified picture of the universe. These mysterious components of the cosmos play a central role not only in science, but also in humanity's quest to understand our place and fate within the universe. If dark energy continues to accelerate cosmic expansion, distant galaxies will eventually move beyond our observational reach. Their light will never reach us. This means that future civilizations might no longer be able to study the early universe as we do today. Thus, the study of dark matter and dark energy is not only a cornerstone of modern science, but also crucial for shaping the understanding of future generations. These investigations also push the limits of technology itself. Building more sensitive detectors, more powerful particle accelerators, and more advanced space telescopes represents the pinnacle of engineering and human innovation. For instance, the James Webb Space Telescope allows us to peer deeper into the early universe, revealing new insights into galaxy formation and dark matter distribution. Every new observation, every new experiment, helps fit another piece into the cosmic puzzle, a testament to humanity's collective curiosity and relentless pursuit of knowledge. The existence of dark matter and dark energy proves that the universe is far more complex and fascinating than we once believed. Realizing that everything we see and touch is merely the tip of the cosmic iceberg deepens our sense of humility. These mysteries inspire scientists to craft new theories, design new experiments, and ask deeper questions about the nature of reality. Perhaps as a result of these efforts, this cosmic journey continually pushes the intellectual boundaries of humankind. Each of us is part of this great cosmic story. Science gives us the language to understand it, while philosophy and art offer ways to interpret and give meaning to it. The dark side of the universe is not merely a scientific problem. It is also a reflection of humanity as existential quest. It compels us to think more deeply, to question more profoundly, and to feel more connected to the cosmos itself. For the universe is not merely something outside of us. It is also a mirror of our infinite curiosity and desire to explore. This vast unknown should not frighten us but excite us, because every mystery opens the door to a new discovery, and the universe is a treasure chest filled with secrets. The universe, as far as we know and understand it, is a magnificent collection of mysteries. Dark matter and dark energy are the deepest and most astonishing among them, the invisible architects of the cosmos, the silent conductors of the grand cosmic symphony. Though unseen, they shape everything from the formation of galaxies to the ultimate fate of the universe. Together, they comprise about 95% of all cosmic mass energy, revealing just how small a fraction of existence ordinary atomic matter truly is. Dark energy drives the universe's accelerating expansion, while dark matter forms the gravitational skeleton that binds galaxies together, the twin pillars of our cosmological model. These discoveries have not only revolutionized our understanding of how the universe works, but have also expanded the frontiers of physics. As we continue to explore phenomena beyond the standard model, fully understanding these mysterious forces may one day allow us to predict the universe's ultimate destiny, and perhaps uncover deeper meanings behind our own existence. Throughout this documentary, we have sought to illuminate the universe's dark side. Through data, observation, and theory, we have examined the strong evidence for dark matter and dark energy and explored their profound impact on the structure, evolution, and future of the cosmos. This journey has been not only a scientific exploration, but also a philosophical reflection, an invitation to rethink humanity as place within the vast cosmic adventure. The secrets of the universe remain an endless source of inspiration. Every new discovery reminds us how much remains unknown and fuels our curiosity even further. Dark matter and dark energy are just the beginning of this infinite quest. When we finally uncover their true nature, we may at last answer the most fundamental questions of existence. Until then, these invisible forces will continue to stand as the most captivating and thought-provoking mysteries of the cosmos. When this dark and mysterious veil of the universe is finally lifted, humanity will find itself part of a much grander picture, one far more intricate, elegant, and awe-inspiring than we can yet imagine. As science continues to guide us on this eternal journey, we will keep listening to the silent whispers of the cosmos and deepening our connection with it. For the universe is not merely outside us, but a reflection of the boundless curiosity and longing for discovery within us.